Look at a deep water offshore platform. In an environment this isolated, a single structural failure or high-pressure gas leak creates an immediate, catastrophic threat to the crew and the facility. The integrity of tens of thousands of individual welds is the primary barrier between stable production and total loss of containment. A common misconception in industrial construction is that a final inspection guarantees a safe product. But quality cannot be inspected into a weld after it is finished. By the time a defect is found on the shop floor, the failure has already occurred. To prevent those failures, engineering teams rely on quality assurance, or QA. This is the proactive, preventative framework established long before the first piece of steel is cut. QA dictates the overall system. It encompasses ISO 9001 quality management requirements and generates the inspection and test plan, a mandatory step-by-step checklist defining exactly how and when every single activity will be verified. If QA is the preventative framework, quality control, or QC, is the reactive execution. QC is the physical process of deploying inspectors to the site to measure, test, and detect specific deviations from the design. The QA engineer works from the office, designing the procedures and auditing the framework to ensure the system is capable of producing sound work. The QC inspector is on the ground, wielding the gauges and X-ray film to verify the actual product against the drawings. Quality assurance writes the rules of material integrity. Quality control provides the physical enforcement. Together, they form a closed, interdependent loop that stops errors from compounding into disasters. This verification loop relies entirely on a concept called Design for Inspection, or DFI. DFI bridges theoretical engineering with physical reality. The core principle of DFI is simple. A design is invalid if its geometry prevents diagnostic equipment from accessing a joint. A theoretical load calculation is useless if the weld holding that load cannot be tested. To test a pipe weld effectively, inspectors need a rigid 150 mm clearance boundary on both sides of the joint. If designers place a weld too close to structural steel, the diagnostic probe cannot reach it, rendering the joint blind to inspection. DFI principles dictate every part of a facility layout. Pressure vessels must be drafted with person entry manholes for internal corrosion checks, and piping systems must be engineered with specific isolation valves to create boundaries for high-pressure hydrotesting. Engineering without considering inspection access creates permanent vulnerabilities. If the inspector cannot prove the work was done correctly, the system cannot be safely activated. This decision tree represents the hierarchy of non-destructive testing. Inspectors do not arbitrarily pick testing methods. The tools deployed are dictated entirely by material physics and the expected morphology of the defects. Every inspection protocol begins at this exact node, visual testing, or VT. ASME B31.3 code is uncompromising here. Regardless of whether a pipe carries inert water or lethal chemical fluid, 100% of all welded joints must pass visual testing before any other diagnostic method is applied. A highly trained inspector, equipped with nothing but a flashlight, a mirror, and specialized weld gauges, can detect 80% of all surface defects using visual geometry alone. They are measuring against extremely rigid limits. For example, if the inspector detects an undercut, a groove melted into the base metal next to the weld, it cannot exceed a depth of 0.8 millimeters. Any deeper, and the pipe wall is critically compromised. Even the environment is regulated. To perform a valid VT, the surface must be illuminated by a minimum of 500 lux, and the inspector's eye must be within 600 millimeters of the steel. VT is the ultimate quality gateway. Deploying expensive, radiation-based diagnostic tools is a waste of time and budget if the weld fails basic visual geometry. Next, the testing matrix splits to target microscopic surface defects. The correct path depends on whether the metal is magnetic. For non-magnetic stainless steel, inspectors use penetrant testing. A highly visible liquid is applied, and capillary action pulls the fluid deep into microscopic cracks. PT requires precise timing. After thoroughly cleaning the steel, the inspector applies the penetrant and must wait for a strict dwell time of 10 to 30 minutes, allowing the liquid to fully seep into the flaws. Next, the excess liquid is carefully wiped away. If the inspector wipes too hard, they extract the fluid from the defect itself. Finally, a white powder developer is sprayed over the area, acting like a sponge to pull the trapped red liquid back to the surface, exposing the exact outline of the crack. Carbon steel requires magnetic particle testing. An electromagnetic yoke is applied. If a crack exists, it disrupts the magnetic field, forcing magnetic flux lines to leak out of the surface. Iron particles sprinkled over the area immediately snap to the flux leakage, revealing the defect. MT is operationally superior whenever the material allows it. It requires no dwell time, making it significantly faster than PT, and the magnetic field can expose near-surface defects that are hidden up to 3 millimeters below the metal skin. Surface testing methods are never chosen by preference. They are an absolute binary choice dictated by the base material's physical properties. Surface methods cannot see the internal volume of the material. To find trapped gas bubbles, porosity, or areas where the weld failed to fuse internally, inspectors must look straight through the solid steel. Historically, the industry's gold standard for internal inspection has been radiographic testing, or RT. RT provides undeniable proof of internal integrity by generating a permanent physical record of the weld. This diagram shows the mechanics of RT. Gamma rays are fired through the pipe. Because internal voids and cracks are less dense than solid steel, they absorb less radiation. This casts darker shadows onto a piece of photographic film placed on the opposite side. But field radiography usually relies on an iridium-192 isotope. This is a continuous gamma ray source that cannot be turned off, only shielded. Bringing it onto a busy construction site introduces a massive safety hazard. The logistics are severe. Safety protocols demand a 30 to 50 meter barricaded exclusion zone around the testing area. Because the radiation would endanger other workers, RT is almost exclusively forced into mandatory night shift schedules when the site is evacuated. RT guarantees internal certainty, but its radioactive nature creates extreme schedule bottlenecks. Modern construction requires a method that maintains accuracy without halting site operations. That alternative is ultrasonic testing, or UT. Instead of firing radiation through the pipe wall, UT uses high-frequency acoustic waves, typically between 1 and 10 megahertz. An inspector applies a transducer to the steel, firing acoustic pulses into the material. When those sound waves hit an internal void, they bounce back. By calculating the exact return time and amplitude, the equipment pinpoints the flaw. UT provides a critical engineering advantage. While an X-ray film only shows a flat, two-dimensional shadow, acoustic pulses measure the exact depth and vertical height of a crack deep inside the material. This comparison illustrates phased array UT. Instead of a single pulse, an array of up to 128 elements electronically steers sound waves in a sweeping radar pattern, instantly generating a cross-sectional image of the weld. This technology is actively replacing traditional radiography. Phased array generates a permanent digital record equivalent to X-ray film, but it emits zero radiation. Inspectors can execute full volumetric scans safely in the middle of a crowded, daytime construction site. Shifting from radiation to advanced acoustics eliminates the exclusion zones and the night shifts. It resolves the tension between verifying absolute integrity and maintaining project velocity, modernizing QA/QC workflows into a digital-first process. Before any of those non-destructive methods are deployed in the field, the exact welding parameters must be proven in a laboratory. This requires destructive testing. Destructive testing intentionally breaks sample welds to extract physical data. Pulled apart in a tensile machine, the steel must snap in the base metal. If it breaks at the weld seam, the engineering procedure fails and is redesigned. Other tests measure resilience. The Charpy impact test strikes a notched specimen with a heavy pendulum hammer at sub-zero temperatures. This proves the specific metal alloy won't suddenly become brittle and shatter during a deep freeze. Inspectors also conduct hardness testing, pressing an indenter into the metal to measure its resistance. They verify the hardness across the unmelted base metal, the melted weld metal, and the heat-affected zone situated directly between them. Theoretical metallurgy is only a hypothesis. Destructive testing is the empirical proof that a weld structure will survive the physical violence of its operational environment. Once proven in the lab, procedures enter the reality of the construction site, where pristine QA plans clash with analog variables. Consider a critical field scenario, testing a carbon steel piping system that will process highly lethal sour gas loaded with hydrogen sulfide. This interface tracks a field hardness survey. The base and weld metal pass, but the heat-affected zone hits 255 HBW. breaching the NACE MR0175 limit of 248. Above this threshold, steel becomes highly susceptible to sulfide stress cracking. Toxic gas will rip the weld apart. The QC inspector has no choice. They immediately issue a non-conformance report, or NCR. This legally halts work on that section and formally documents the code violation. Engineering cannot accept this weld as is. It mandates a physical disposition. The crew will have to execute a re-post weld heat treatment, systematically baking the joint at a high temperature to temper the steel and force the hardness back down to safe levels. That NCR data doesn't just sit in a file. It is fed back into the quality assurance framework to identify exactly why the heat-affected zone hardened in the first place, triggering adjustments to the welder training program. Quality is a continuous, data-driven cycle of prevention and detection.